Okay, welcome once again to our lecture on the s- sketching, curve sketching. So last time we have this part, ended our discussion last time here, and we have another example here, class. For your just do the same, just follow the procedures in solving this problem for our example number two. So I will leave it for you to practice. Now, let's continue with our discussion. We have another term here. We called it concavity. All right, so this is also a very helpful terms, no, to help us sketch the curve. So we need to know the concept on the concavity. So we have here another definition. So the graph of a function f is said to be concave upward at point C, at point of tangent C, with coordinates C, f sub C. If So these are the conditions. If prime of C exists and there is an open interval I containing C such that for all values of x in the interval I such that x not equal to C, the point with coordinates x and f sub x is above the tangent line to the graph at this point of tangent C with coordinates C, f sub C. In our illustration here, alright, so the interval, the point is above the tangent line. So if you look at this, so this is our tangent line, this is our graph. So we can say that the point is above, no? Above the tangent line. So for this particular graph, so we can say that the point is above the tangent line. And so do with this problem, or sorry, for this illustration. Okay, so that's concave upward. So these are the conditions. So uh, to remember it, if the point of tangency is above the tangent line, then we can say that the function is concave upward or concaving upward. All right, now for the opposite scenario, so the graph of function f is said to be concave downward at a point with the coordinates. So in this case, this is our point of tangency with coordinates c, f sub c. So in this case, this is our point, coordinates this one. So the condition is, or the conditions are the following: A, f sub c exists, meaning if you substitute the value of c into the first derivative of the function, if it exists, okay, so this condition is satisfied. And second condition, there is an open interval I containing C such that for all values of x in the interval I such that x not equal to C, the point, so this point, coordinates x and f of x is below the tangent line to the graph at this point of tangency with these coordinates. Okay, so if you look at this, just to summarize it to help you remember easily. So if you look at that, the point is below, no, below, the keyword here is below the tangent line, because this is our graph. Okay, this is our graph of the function, and of course the point of tangency is here. So when you draw the tangent line, so we can say that the point is below the tangent line. Okay, so in this scenario, in this picture, we have the point below the tangent line, and so do with this one, because this is our graph, this is the point of tangency, this is our tangent line, so we can say that the point of tangency is below the tangent line. Okay, so in this case, we can say that the function is concave downward. All right, so remember this, class. This is a very important concept to help us draw our function. So let us test your understanding. So determine which of the following graphs are concave upward or concave downward. So how about this? Okay, so you just find the tangent line and look at whether the point of tangency is above or below the tangent line. So in this case, our tangent line is something like this. Uh, Perhaps this is the point of tangency here. Okay, it's a point of tangency, and then our tangent line is something like this. So we can say that the point of tangency is above the tangent line. So we can say that this is concave upward. So in this case, so this is our point of tangency. So perhaps somewhere here, the point of tangency here, and then when you draw the tangent line, so we can see that the point of tangency is below the tangent line. So this is concave downward. And so do this one. Okay, this is concave upward, this is concave downward. Now we will use the concavity test now to help us able to determine whether the function is concave upward or concave downward. So in this case, class, we use the secant derivative. Okay, so we have here a theorem that if we let f or let the function be a function, let f be a function which is differentiable on some open interval containing c, then if the double prime of c, meaning you take the secant derivative of the function and then substitute the value of c on the secant derivative and determine if the result is positive, meaning greater than 0. So if it happens that the secant derivative of the function at c greater than 0, then the graph is concave upward. Okay, so if the double prime or the secant derivative is positive, then we can say that the function is concave downward. And b, this is the opposite. Now, concave downward if the secant derivative, when you substitute the value of c, is negative, will give us the negative result. So it means that the graph of f concave downward at the point of tangency. Alright, so that's the concavity test. And we also have another term, we call it point of inflection. So what is this point of inflection? This is the point, class, where the concavity changes from concave downward to concave upward or vice versa. So that point where the changes or the change of concavity happens or occur, so that point is called the point of inflection. Alright, so we have here another definition. So a point is a point of inflection of the graph or the function f if these conditions are satisfied. So for A, we have the graph has a tangent line at the point of tangency, coordinates c f sub c, and there exists an open interval I containing c such that if x is in the interval I, then either uh, the double prime of x is negative or less than 0 whenever x is less than c, and if double prime of x greater than 0, meaning positive whenever x greater than c. Alright, so we have here a representation for this scenario. Okay, or f double prime is positive whenever x is less than c. Same condition here above, x less than c, here x is less than c also. Alright, and if double prime is negative, so whenever x greater than c. Right, so we have here this illustration to emphasize this part here. Okay, so this is the definition of the point of inflection. Now we have here some illustration to give us more emphasis on this term point of inflection. Alright, so in figure 4.36a, so meaning this figure here, So take note, this is the point of tangency. Or sorry, this is the point of inflection. So the point where the concavity changes. Now, in this case, this is concave upward. So we have this point, and then it turns to concave downward. So this point here is what we call the point of inflection. Coordinates C and F sub C. Right? And so do with this part here. Figure 4.3.6b. Okay, so in this case, this one is concave downward. This point, the point of inflection, it turns to concave upward. Alright, so these are some illustrations of the point of inflection. Okay, so next we have what we call the second derivative test for relative extrema. So a while ago we discussed about first derivative, to test the relative extrema. So this time we will use the second derivative test to determine the same thing. That is the relative extrema. That is the relative minimum and the relative maximum. So the theorem here. So let C be a critical number of a function f at which f prime of C is equal to 0. Alright, then suppose further that f double prime exists for each value of x in some interval containing C. Alright, so satisfying this condition, we have this theorem here. If the second derivative of the function at x equal to C is less than 0 or negative, meaning the second derivative is negative, then f has a relative maximum. So take note on this class, and just compare the first derivative test with the second derivative test. So in this case, if the second derivative is less than 0, meaning negative, then f has a relative maximum at C, maximum value at this particular value C. Otherwise, if this is positive or greater than 0, then the function has a relative minimum at C. Okay, so it's easy to remember, class, for the second derivative test. If the second derivative is negative, so meaning maximum, relative maximum. Uh, Otherwise, if this is positive, first, condition A, theorem A, if the second derivative at C is negative, less than 0, relative maximum. The opposite is relative minimum. If this is positive, the f double prime of C is positive, then it has a relative minimum at point C. Or, sorry, at number C. Okay, any question? So we will combine all these concept, class, to analyze, to help us sketch the curve. Now we have here our next example. So example number 1, again we will use the same function equation. So we're given here the function f of x, function of x, 2x cubed, 2x cubed minus 6 plus 1. So we are asked here to determine the intervals where the graph of f concave upward, concave downward. Also determine the inflection points, or the point of inflection, or points of inflection of the graph of f, if any. So meron man, so we have to find that also. Okay, so again, this is our solution, class. Step number 1, we need to find the second derivative. Of course, before we can find the second derivative of the function, we have to pass through the first derivative. So we solve first the first derivative of this function. So that is 6x squared minus 6. Now, for the second derivative, so simply 12x. So when you equate this to 0, okay, so we can say that, so find f double prime x and equate to 0. So when you equate this to 0, because we're looking at the maximum or minimum. So at x equal to, I mean, if double prime of x equal to 0, so we can solve for x from here. So 12x divide 12 both sides, so 0 over 12, so that is still 0. So therefore x is equal to 0. Now the next step, consider the interval determined by 0. So what are the intervals? Okay, so the intervals, if this is your 0 here, okay, so we have here the interval, this part here and this part, so which is negative infinity and 0. So this is open interval. And we also have the other interval, this part and this part here. So take note, to the right we have the positive infinity, and to the left we have the negative infinity. Okay, so this is 0 and positive infinity. So these are the intervals. All right. Mhm. Okay, so these are the intervals. This is the result of our step number 2. Then determine the sign of f double prime of x in each interval and apply the concavity test and the secant derivative test. Okay, so now we can summarize it in this table. So we have here the interval, negative infinity 0, we have 0 infinity, then at x equal to 0. So we solve for the double prime here, double prime of x, f double prime of x. Alright, so we have here for this interval, the secant derivative, we have 12x. So when you substitute values in this interval, what are the values? For this interval, you can substitute negative 1, negative 2, negative 3, and so on and so forth. So when this is negative 1, so we have negative 2. So this is still negative 12 times negative 2, negative 24. So your secant derivative here as a function of x is always negative. So therefore, if this is negative, as mentioned in the theorem, so it means that f, meaning the function, concave downward, right? If this is negative. Now at x equal to 0, so at x equal to 0, we can solve for f of x. So f of x is equal to, substitute here. So we have at x equal to 0, our f of x is equal to 1. Then our f prime of x is negative 6. And then f double prime is 0. So since we have a 0 here for our double prime, so the graph has a point of inflection. Okay, so there's a changes to the point where the concavity changes from concave upward to concave downward, or vice versa. Now for this next interval, 0 and positive infinity, so we have to determine the value of our, or the sign of our f prime of x, whether it's greater than 0 or less than 0. So what are values that we can substitute to our secant derivative now in this interval? So we can have 1, 2, 3, 4, 1000, and so on and so forth. So we substitute that value in this equation. So all positive values will give us the positive result of the secant derivative. So therefore, secant derivative is, as a function of x, is positive. So positive, it means that the graph of the function f is concave upward. Okay, so that's how to analyze the given function. So that gives us, or help us figure out how our function looks like, how it looks like, the given function. All right. Now to summarize this, so interval where graph of f is concave upward. So given in the interval here, so concave upward at this interval, 0 to positive, 0 positive infinity. The interval where graph of f concave downward, okay, downward. So here, this interval, and the point of inflection, so that is if double prime is 0. All right, so when x equal to 0, what happens? Our f of x is equal to 1, so 0 and 1. Okay, so this is the point of inflection. So sketching the graph of a function. So we'll go now to the sketching. So in order to make the graphing of a given function easier, so we need to summarize the things we have done as follows. Okay. First one is solve the f prime of x and also the f double prime of x, mean the first and the second derivative. That is the first step. Huh? We are now in the sketching of the graph of the given function. The second one is to consider all the critical points or the critical numbers of f and the solution to the equation f prime of x equal to 0. Then arrange these numbers in natural order. Okay, then after that, obtain the intervals determined by these numbers. Because, through this critical number, we can obtain the intervals determined by this calculated or resulting critical numbers. Then for step number 4, apply the theorems. So what are those theorems? We have the theorems on increasing decreasing test, theorem on concavity test, and the theorem on the first and second derivative test for relative extrema. All right, so these are the things that is indicated in step number 4. All right, so now let's do the same example class. So as you have noticed, we are keep on using the same function. So given function f of x equal to 2x cubed minus 6x plus 1. So here in this problem we are asked to sketch the graph of the function f defined by this equation. Alright, so actually class, this is the combination. To solve this problem, we need to combine all those things that we have just discussed. Alright, so our ending here is a graph of the given function expressed in this equation. Okay, so solution. So step number 1, we have to solve for the first derivative and also the second derivative. And after that, for step number 2, we have to solve for the value of x. For we will make it f prime of x to 0. Then you can solve for x and also set the f double prime of x to 0 not to determine the point of inflection of the critical numbers. So in this case, so we have two values for x here, that is x equal to plus and minus 1. Here for the critical numbers, for the point of inflection, we have x equal to 0. So from this, we can arrange these numbers in a real number line so that we can determine the intervals. Okay, so this is the number line system. So we have plus and minus 1. So minus 1 here, then x equal to 0. Okay, so these are the reference value, so that we can create some interval where we can observe the behavior of the function, whether it's increasing or decreasing, or whether it concaves upward or concave downward. All right, so in step number 3, so out of these numbers, so we can be able to get the intervals, right? So on the left side of -1, so we have one interval on this part, which is this one, negative infinity, -1. And then between -1 and 0, so we have this interval. Okay, so another interval here, Then between 0 and 1, so we have this interval. So that's why we have interval 0, 1. And we also have the interval from this part here to the rightmost. So we call it positive 1, positive infinity. So far we have 1, 2, 3, 4. So we have 4 intervals. So we are going to examine now using the different concept, the test, increasing and decreasing test. We have the first, the second derivative test, the concavity test. So we will apply all those principles, no, to help us able to sketch the graph of the given function. Okay, so step number 4. So we have here the function, given function. We have here the first derivative, and we have here the second derivative. So we wrote this, for our reference, for our references. Okay, and then create this table. So creating this table, for this interval, negative infinity, negative 1 for this first interval. So we are going to substitute values within this interval. We will get the first derivative. Now, whatever values you are going to substitute within this interval, it will always give us the first derivative that is greater than 0, meaning positive. And the second derivative, it will give us negative. So therefore, we can say that, no, from our theorem, if f prime of x is positive, meaning greater than 0, it means the function is increasing, right? And for double prime of x, if this is negative, so it means that the graph concave downward. All right, so that's it now. That's what you are going to remember. If this is positive, increasing. If this is negative, decreasing. For concavity, if this is negative, concave downward. If this is positive, then concave upward. Okay, now so we have here the value of x equal to minus 1. So let's find the value of f of x for x equal to minus 1, so that we can uh, have some reference point, no? Because we have here the point coordinates negative 1 and 5. So this is a very important point. No? We have to determine if that point is maximum or minimum or not. But using the first derivative test, so when you find the maximum or minimum value, or the relative extremum, relative maximum, or relative minimum, so we have to equate this f prime of x equal to 0. So this should be equal to 0. And then determine our second derivative. So our second derivative is negative. So therefore, so f has a relative maximum. Okay, relative maximum at this point, coordinates minus 1 and 2. So this is a maximum point. So it has a relative maximum value. Okay, then okay, so negative. So it means that is still concaving downward. No, if double prime is still negative. So there was no change of the concavity yet. Now for this interval, negative 1, 0. Okay, so let's determine the sign of the first derivative. So we have to substitute values within this interval. So what are values that is within negative 1 and 0? So perhaps you can have um, 0.5, right? You can try 0.5 or any values within this negative 1 and 0. So you have negative 0.5 and you have positive 0.5. So when you substitute that value, it will give us a negative. So our f prime of x is negative, and it will also give double prime of x negative. So therefore, if this is negative, so it means that the function is decreasing. All right. So this is still negative, so it means that the graph is still concaving downward. All right. So now for x equal to 0, so for x equal to 0, again we have a critical point here. So at x equal to 0, substitute the x equal to 0 to the function, and it will give us 1. Alright? Then solving for f prime of x, it gives us negative 6. Okay, so negative 6, so our f prime of x is negative. And then if our f double prime of x equal to 0, so it means that this value, the graph means, it means that the graph has a point of inflection. Okay, so this is a point of inflection, x equal to 0, f of x equal to 1. So this is the point where the concavity changes, from, in this case we have downward and then now positive, so it will be upward. Okay, now for this interval 0 and 1, so we substitute values that is within 0 and 1. Perhaps you can assume positive 0.5, then find out what is the value of f prime of x. So when you substitute that to our f of x, it will give us negative. Now, whatever value is that is within this excluding 0 and 1, say 0.1, 0.999, so it will always give us negative, meaning less than 0 of our f prime of x. So it means the function is decreasing. But if you solve for f double prime of x for that value of x, which is equal to 0, so it gives us a positive. So positive, so it means that the graph concave upward. Okay, so the graph concave upward. Now for x equal to 1, okay, so this is the last critical number. So solving for f of x, so it gives us negative 3. And when you solve for f prime of x, it gives us 0. So it means this is a minimum value. So f has a minimum value. Alright, and f double prime here is still positive, so it means it's still concave upward. Now for the last interval, 1 positive infinity, so we have here f prime of x that is positive, so positive meaning the graph is increasing. Then our f double prime of x is positive, so it means the graph still concave upward. Okay, so that's the, and then after this we can graph the function, or sketch the graph of the function. Just to summarize now, these are the conclusion part. So to summarize, now to give you an idea on how to graph the function, okay, so we have here, in this case, it means that our function, the arrow going down means decreasing. So in this particular graph, we can say that the function is decreasing, that is indicated in this arrow, decreasing. So it means that concave downward. On the other hand, if you have this kind of graph, it means that the function is increasing and still this is concave downward. So another possibility is something like this. If you can see this, if the function is increasing, okay, so we have this possible scenario, so concave upward, or something like this. If you have a graph like this, so it means that the function is decreasing, but still this is concave upward. Okay, now uh, to summarize, so to graph this, so we have, of course we need to plot the points. These are the critical points. We have negative 1 and 5. Okay, negative 1 and 5, so this is our point. Then we have another point here that is 0 and 1. So 0, x0, f of x is 1, 0 and 1. So this is a point of inflection. Okay, this point is the point of inflection, that is the point where the concavity changes from concave upward to concave downward, or vice versa. And another point here is this one, when x equal to 1, so we have f of x equal to minus 3. So this is the point here, and these are the coordinates. Now using the interval, Okay, so we can say that for this interval negative infinity to negative 1, so since f increasing, graph concave downward. Okay, so we have followed this. Okay, so that's why we draw something like this. All right, the next we have at this point x equal to minus 1, our f of x is 5. So this is our maximum value or maximum point. Then the next interval is negative 1, 0. So negative 1, 0. So negative 1, 0, we have the result here decreasing. Our f is decreasing. Graph concave downward. So decreasing concave downward. So this one. So we use this. Okay. Next, at this point, so graph has a point of inflection. So at x equal to 0, f of x 1. So meaning at this point. So at this point, there will be a change of concavity. So this is the point of inflection. So in the next interval 0 and 1, so meaning in this interval here, so we can say if decreasing, graph concave upward. So decreasing concave upward, so it means we have to use this. So f decreasing concave upward, so this graph here. So therefore, so we have that particular curve. So a while ago, for this interval is concave downward, now it concaves upward, so this confirms our point of inflection. And then at x equal to 1, f of x equal minus 3, so this one. And f has a relative minimum, so this is a minimum point. Now for the next interval 1, positive infinity, so we have noticed here that f is increasing, graph concave upward. Increasing ang f, concave upward, so we have to use this. Okay, so using this, therefore we have this one. So you see, we're able to sketch the graph without providing values of x and then solving for f of x, but we just use the theorem. All right, so I hope you're able to catch up, no? And this is the actual graph of the given function. So in summary, so we have here that the function is decreasing at this interval, okay, and function is increasing at which interval? So here, so in increasing, you see here for this interval, increasing our function, as well as at 1 positive infinity, 1 positive infinity. Function is also increasing, so we use the symbol union, meaning this the values within this interval together with this values in the interval, the function is increasing. All right. Now we have here concave downward. So when was the function concave downward? So we have here at this interval negative infinity 0 and negative infinity 0. Okay, so concave downward you see here. So at this point, so negative infinity to 0. All right. Then for concave upward, so it means here going that way, that is interval that is 0 to positive infinity. Then we have the relative minimum point. So relative minimum point, of course, so from the graph we can see it here. So at this point here, okay, so that is 1 and negative 3. Okay, so 1, negative 3. So at this point, and we have the relative maximum. So of course there's no other point here, so except this one. So this negative 1, 5. Okay. Then we have the point of inflection. So point of inflection is the point where the concavity upward changes to concavity downward, or in short, is the point where the concavity changes either from upward to downward or downward to upward. Right, so that is at point coordinates 0 and 1. Okay, so that's it. So I hope you can be able to solve similar problem class and finish the solution up to this point. Just first you have to show your estimate of the sketch of the graph, and that would be enough already. And then after that, you just use that graph, to summarize all these things. Okay, so thank you very much, and I hope you will practice, just solve the same problem, this problem example number 2 and 3, using the same procedure. All right, so that's all. See you again on our next topic. So I think that would be the uh, application of the derivative, all about maxima and minima problems. Okay, thank you very much, class. See you in the next video. Stay safe and healthy always. Bye.